Good to go. All right. How's everyone doing today? Having a fun time at Secure West Virginia? I suspect that many of you have been to HackerCon, is that correct? Raise your hand if you've been to HackerCon. All 5 years. I love this conference and this general group of people. So let me get started here. So my name is Jon Schipp. I'll be talking about a group that I've developed and I've been working with and its projects as well as some technologies that we're using to facilitate its needs. Also, I am a security engineer at the National Center for Supercomputing Applications. We do high-performance scaled computing for scientific research. We have one of the world's fastest supercomputers. There's like 800,000 nodes, etc. It's this huge machine that takes up this enormous facility. And on the side, I have my own consulting company called Draconics that specializes in web hosting and providing security, network security monitoring that is managed, and other sort of development and full-service IT solutions. So a number of projects that I've been contributing to is the Bro project. I'm on the Bro team. I do a lot of miscellaneous things. I've also made a number of commits and patches to the NetSif NG toolkit, Security Onion, the popular NSM-based Linux distribution, and now what I'm going to talk about today is just OpenNSM. And you can see a general theme here that everything up here, if you've heard of these tools, is they're all NSM focused. That is network security monitoring. Because that's what I really like to work on. And perform operationally. So, this entire talk, again, is based on the work that's coming out of this OpenNSM group, which stands for the Open Network Security Monitoring Group. And this is a group that is at the University of Illinois in Urbana-Champaign. And it's a weekly NSM digital forensic incident response group. We have remote attendance available, so anybody in the audience can attend from anywhere. So there's really no boundaries or geographic borders. We do have international participation. We have a guy from Scotland. We have someone from Columbia, all professors and such. And we have a lot of people from industry that help out. So if you'd like to learn more about this group, check us out on open-nsm.net and on Twitter at OpenNSM. So why did I start this group? Well, I've always loved OpenNSM. I don't know if you guys ever heard of Richard Batelich, but he's written the tome of the network security monitoring practices and procedures in a book called The Tao of Network Security Monitoring. And he's one of the leading NSM strategists out there, and he's now working for FireEye. So in his most recent book, he suggested that we have some sort of NSM group for collaboration and sharing of knowledge for defensive practices in our networks. Just like we would have those same types of groups in other areas, such as Linux user groups, or BSD user groups, or a Java user group, or whatever. Just get a number of people, put them together, and work on projects. And so I took this up. I thought this idea was a great idea, and I already run a number of different groups and have over the past. And so I was like, I can do this. And what's more is that there really doesn't exist, that I found on the internet looking around or talking to people, another NSM focus group in the United States. I may have missed one, but I did search hard and I could not find any. So I think we are the first one. And so the problem with this is that they're not spawning up all over. So I try to make this the premier group, that is the group that anybody, if you don't have one in your local area, you can just come to us. Or not, you don't have to, physically come to us, but you can connect to our meetings, talk to our people, and work on our projects. So it's very open. Again, the Open NSM group. And we have a really good community, a network security monitoring community at the University of Illinois at the NCSA. For one, the Bro network security monitoring platform is developed at the NCSA. Has anybody in here heard of Bro? Is anybody do intrusion detection that has not heard of Bro? Because I highly recommend you check that out. It's a very powerful scripting language for analyzing and working with packets. You can write awesome detections using Bro. So it fit really well right here in this central Illinois area. And that's why I created OpenNSM. So where does the group focus? Well, obviously to share knowledge, to develop software. There is a number of needs in the NSM community that I've seen that, this tool doesn't do what I want, or I'm not able to perform this in the way that I would want to perform it. Things that make your life hard. And what if we can using this group, facilitate a number of people working on different tools to address problems that happen in the community? So we're working on a number of new tools, especially in training and stuff, which I'll get into shortly. Also, we are looking at research. Since we do stuff at scale at NTSA, I've become more interested in performance. So we plan to conduct research on various tools on various system specs and finding out what is the best approach or best settings for a particular type of traffic that you want to analyze. Things like that. So the current projects that we have are ContainNSM. ContainNSM is a project where we are Dockerizing or building containers out of all the popular NSM tools at major releases and minor releases. So the idea is that we have one central location where you can go and you can pull down TCP dump at version XYZ or snort at version XYZ and run it on your computer without having to go ahead and compile the source yourself and deal with all that. So the other project we have is FuzzNSM. This is a project that we are actually trying to fuzz and find vulnerabilities and bugs in various NSM tools. So I know right now Justin Azoff at the NCSA is working on this, and he's been fuzzing Bro, and he's been fuzzing Sagan, a multi-threaded log analysis engine. And we hope to scale this out in some way. It turns out that fuzzing stuff with libpcap is very hard. So we got to find ways to get in actually instrument the binary to get in, or instrument the library to get in the code, so we can actually focus on the application layer data. Rather than all the functions that we have to get to open and close the PCAP and blah, blah, blah. Third, we have another project called Doku. So we are working on building a malware analysis tool. This is more of an experimentation for, well, I should say, to contrast with the virtual machine-based malware analysis tool like Cuckoo, we're trying to do it in Docker containers. So it opens up a number of explorations in security, too, and how well that interacts with the kernel and the constraints you can put on those things. So we are playing with that. But the idea with this tool is that when you're working with Cuckoo Sandbox, for example, if you have a lot of pieces of malware coming across the network, say hundreds or thousands, because it's a large enterprise or a large organization, and you need to pull those out with, say, Bro, and you want to ship them off to, using like an API, ship them off to Cuckoo for analysis, you better have a really beefy machine or a cluster of really beefy machines to be able to facilitate thousands of pieces of malware where a VM spins up, the actual piece of malware goes into the VM, it's analyzed, the Python agent sends it back to Cuckoo Sandbox manager, it writes the reports, and all that. And you can't really do that to scale well. So we're using Docker containers, which have a very fast startup time, or containers in general, in milliseconds is rated. We can hopefully be able to run, and I really expect this, once we get a proof of concept complete, to be able to take in thousands of pieces of malware a second and be able to run them concurrently. Also, I am working on the groups, I should say, is working on a NSM video training course. So if you're new to NSM, you want to get involved, I have a channel on YouTube where I've developed 30-something videos so far to take you in the ins and outs of various tools. Right now we have the TCP module almost complete, the TCP dump module, and it goes a lot of detail in TCP dump. And I'm working on the BPF and Docker modules next. All right, so now we're going to get into more technical stuff. That may have been a little boring. But I should ask, actually, which I didn't before, is, has anybody heard of the Open Network Security Monitoring Group outside of this room? Or inside this room. I don't know why I said outside. Thank you. You worked on that. Yes, very cool. Yes, I remember. He actually gave a presentation. Is it Josh? Sean. Sorry. Yeah, Sean gave a presentation for us one time last year. So I do thank him for that. All right, so we're talking about the Linux containers, the technology behind all the tools, or a lot of the stuff that we're doing. And mostly this comes about because I lead the group, and I've been playing with them a lot. I developed a tool called ILET. I've spoken at a number of conferences about ILET. It's being used in different organizations for training with containers. So I'm kind of keeping that progression, with my interest right now in the past year and a half has been solely on containers. So why would we want to use containers? Well, here's a few things. For one, they provide a level of isolation in your operating system. So if you're not familiar with the way it works, so containers have been around for a long time, but in the Linux container implementation, you have what we call namespaces and C groups. So these are kernel level code that are able to, namespaces to isolate a part of your system, and C groups to be able to apply controls to those namespaces or anything on your system. And so like systemd, the new init system on Linux, for example, just uses C groups by default. You don't even have to mess with containers. It's able to have a more fine-grained control on your processes. So we can have a number of different, there's a number of different namespaces available, which we'll talk about in detail a little bit more later. Also, so we can have this level of isolation, And one thing about this is that it's very lightweight. If we go down to the third point here, that the startup time is in milliseconds. And that is because we don't actually have to virtualize the hardware like you do with virtual machines. You have to talk to a hypervisor, make calls back, translate instructions back to the kernel and the actual guest operating system, etc. Here, you're actually abstracting the operating system. You're dividing the operating system into pieces, not a computer in pieces like you do with virtual machines, if that's one way to conceptualize it. And with this, whenever your application makes some function call or system call, it talks directly to the kernel and the host operating system and returns back to that application. So you don't have to go through the details of going from the application in the guest to the kernel in the guest to the hypervisor and then back to the kernel in the guest, then back to the application. You cut that big hypervisor part out, and it's actually results in a speed up, right? Because then you don't have to do scheduling in the hypervisor, etc. So, continuing along, so we have this lightweightness actually ends up giving us a performance benefit for one. And another thing to talk about the lightweightness of these containers is that this isn't true for all implementations, but in the Docker case, that if you pull down a Docker image of Debian or Ubuntu, you actually have a very small image in the hundreds of megabytes, and you'll notice that if you type man some tool, it'll say man doc not found, or man not found, and you don't actually have the man doc package installed. So it's very lightweight, very condensed. You can add things as you need them. And this is perfect for things we're looking to do to package things up in small ways to just transport them to other people. So with this lightweightness also comes a higher density of operating systems per machine. So we can run thousands of these containers on a system concurrently, where you might not be able to do the same thing with virtual machines because they're more resource intensive. Security. So this is one of the things that's been interesting about containers is that it's still unclear, well, unless you're probably developing on them, but I'm doing a lot of research in the security of them, but they are less secure than virtual machines. Again, because the most obvious reason is that you share the host kernel with the container, right? So if there's a vulnerability, or in the libraries at source in Linux, so there's a vulnerability in libc or in the kernel, and you can execute that in a container, then you can compromise the entire host. Whereas in the virtual machine case, you pretty much have to compromise the hypervisor. If you compromise the host in a virtual machine, you are probably you're more abstracted out so that you cannot compromise the guest VM or the host VM, for example, just the guest. Moving along, so they are less portable across different types of operating systems. This is one bummer. So a lot of different operating systems have their own implementation of containers. Containers are relatively new compared to the other technologies, which we'll talk about more in a little bit. But within an operating system, such as Linux, where we use Docker, they're portable between the different versions of Linux, or at least pretty portable. Concurrency. So again, some implementations, like Docker, are designed to run one process at a time in a container. You don't actually have to do this, but one of the limitations is there's no init system by default in a container. So if I run the container and tell the container to run the command ls, it's going to enter the container, run ls, then exit. There's no other process keeping the shell open, or there is no shell really. So you have to find a way to run multiple applications in a container at once. You have to find a way to do this, and to do that, you need some sort of process manager like an init system. But you can do this because there's plenty of ones like such as SupervisorD. It's a small init system you can install in your container and tell it to launch other processes and keep them open so it manages them, etc. The LXC implementation, the Linux Containers project, doesn't really have this limitation. Or I shouldn't say it is a limitation, but you can get around it. But LXC doesn't have that. They kind of give you a full-fledged OS in case. And lastly, since the containers use the same kernel version as the host, then you cannot really test across different kernels. You have to use the same one. So, like in virtual machines, you want to test your application in a number of different kernels, or you want to play with security research on a kernel, different kernels. You can do that in virtual machines because each virtual machine has its own kernel, right? You can run Linux kernel 3.7 here, Linux kernel 2.8 here, whatever. And in case of containers, though, you can only run the kernel that your host is using because, again, you share the same thing. So those are some of the limitations. All right. So now to get into a little bit more about these things. I think I hear kernel developers say Linux-based containers as the terminology to use because there's a number of different implementations. There's no specification to describe, like, in the kernel, like what consists of a Linux container. It just takes two building blocks and puts them together. And again, those building blocks are namespaces and C groups. But as of recent, there is a specification for runtime implementation. So came out from the CoreOS group. You guys ever heard of CoreOS? As an operating system designed for management of containers. And they called it, they worked on it before, it's called AppSec. And now I think it's called the Open Container Specification, OCS. So this technology has been around for a little while now, and even farther back in the other operating systems. For example, before Linux had them, the BSD family of operating systems had jails. You can run jails on FreeBSD, for example. Solaris had zones. Solaris has been around for a long time for old Unix admins. And same with AIX. AIX has what they call work partitions. So these are all the same conceptual technology, just different implementations in different operating systems, and they are more or less mature than each other. So you can't really compare apples to apples here. It's making a lot of headway in the Linux world, though, because Linux is now the most popular, I think, operating system for the kind of stuff that we do, especially, and in development and stuff outside of Windows. You don't see a whole lot of people using the other ones anymore. It's a shame for some of them, but Linux is gaining a lot of momentum, and it has over the past 10 years. So you're seeing this trend now in Linux, which I can just go ahead and move to the... Oh, actually, I have that 2 slides. I don't want to skip that. But there's a trend. You can see the growth from, like, I think it's like 2007. It's almost a linear growth. If you graph it, I have a chart with Google Trends, I think, in one of my slides here, that shows this Google queries for, like, Docker. And it's gaining a lot of momentum right now, especially among the web application community. So, just to reiterate 2 last points on this slide, that I really want to hit home is that these containers do lightweight process virtualization, also known as operating system virtualization, where the actual virtual machines do a level of hardware virtualization. So it's more nitty-gritty in the virtual machines, and it's at a higher level with the containers. Just kind of remember that. You don't have to do as much work in containers as you do with virtual machines. And we'll do a bunch of demos later to make this more fun. Promise. So, more Linux kernel stuff. The Linux kernel 3.8 introduced these, I think, a mature, at least, implementation of the building blocks for containers. And that, again, is the namespaces and C groups. So, talk about namespaces. So, there's a number of different namespaces available. You have the PID namespace, net, mount, and a few others. So, just to give an example of the names and how they work. If you have a process, okay, and you assign it to a namespace, and then you have another namespace with another process. If you type PS in this namespace, you will not see the process running in this namespace. That is the isolation level. You cannot see, you cannot control, you can't kill the process in this namespace. For example, in chroot, since they don't have that namespace isolation, you can get root and chroot, and you can actually kill and see processes outside of the chroot, right? So this provides a more detailed level of security. So the kernel basically just wraps things up in its own tight-lit box. All these processes are in this box in namespace 1. All these processes are in this box in namespace 2, etc. And you can do this for the network. You can actually have a specific IP address in namespace 1 and another IP address that can only communicate in namespace 2. So that's pretty cool, right? And so on and so forth. You can do it for mount points, etc. So the control groups are a way to do resource management on these containers. So if you have a namespace with a number of processes in it, you can say, hey, these processes in this namespace box, you cannot use more than X number of CPU, right? So you're playing a resource constraint on that namespace. And that's kind of where the C groups come into play. All right, so again, here's that chart I was talking about. I got a little ahead of myself. You can see the growth there. Actually, I got the dates really wrong. But 2013, you see the large jump. And it's a significant jump now. And I should probably redo this graph. I think I did it last year. So, anyway, so Docker is really the one that's been driving the momentum for this because they provided an easy way to implement, create, and deploy these containers. It's not magic. It's actually very simple. You just use a command line tool and you can create these things. All right. And a research moment here. There was an IBM Research report that came out, I think, 2 years ago, where they did a performance comparison between virtual machines using the KVM hypervisor on Linux and using Docker. And they compared different applications, such as, disk-based applications and memory-based applications like MySQL, Redis, etc., and did performance metrics between the two, and they found that in every case, or almost every case, Docker either stayed the same or exceeded the performance that it was in the corresponding application in the virtual machine. So do check out that paper if you're interested in more information. All right, so now we're getting down to more of the fun stuff. So ContainNSM, this is this project that I talked about earlier where we're creating a large repository of different images for network security monitoring. And here's an example at the top. You can see that I'm running a for loop across a bunch of Docker images tagged as bro, and then I tell it to run bro -- version, and you can see that it ran that number of containers in the output, what is it, 8 there, and with different versions of bro. So this is a project to create, Docker images of all the available free open source network security monitoring tools for research, comparison, and training. All right, so we want to be able to make it easy to run and deploy these images with debugging information. So this is one of the development aspects of this program. We want to be able to, developers to be able to run these different tools and kind of compare them, kind of see what's wrong, what I need, what's missing in this tool versus this tool. We can add the information. Or I found a bug in this one. I need to iterate over it till I find a fix, etc. So basically a way to quickly replay these things. Also, we can do research. We can compare, we isolate the application in a container so that there's just that tool in the container and then the basic file system for that Linux distribution. Then we can kind of take away some of the complexity in, I think, performance measurements. And also training. We can easily package these things up and share them with other people with different data sets. Okay, so the roadmap and status. So I developed over 100 images of these things so far. Snort, Bro, Suricata, NetSif NG, Argus, T-Shark, etc. And the other big thing was we went to develop a command line tool called ContainNSM for easy use. And I actually had time yesterday, and I cranked out a proof of concept yesterday, which I'll be demoing today. And we are going to collect data sets so that we can easily integrate these containers to actually, hey, I want to run this version of TCP dump from X number of years ago on this PCAP, get the results, and see it. And we also want to be able to provide users to provide user-contributed configuration. So if you run Snort in your organization, for example, or you have Bro and you have different policies or configuration files, and you want to pass them to us, we can put them in a directory so anybody can easily run that version of Snort that they want to run with that configuration and get the results. Then we can share and test on different types of data sets, the different output. All right, so if you would like to get the ContainNSM stuff, you can clone this repo right here at github.com/open-nsm ContainNSM. And actually, before we continue, I did forget to mention a few things. Let's back out of here. So we do have a GitHub page. You get all of our stuff is on here so far. And if you would like to contribute to the group, do send me an email. I can get you access, and you can begin working on some of this stuff. So we do have, I've set a video course. If you go to youtube.com, OpenNSM, here's the playlist here. So here's our NSM video drafts. I have probably 100 and something more videos to make, but if you do check out this page, you can see these are in order, and you can go through and learn various aspects of various tools. It goes through protocol analysis, being able to dissect or look at packets in hex and understand what at least basic portions of them mean, without having to translate it with a tool. You can do it yourself. Talks about the sequence numbers, acknowledgement numbers in detail, using TCP dump and a bunch of other stuff. Learn about how to create sockets, what sockets are used whenever you're actually writing a sniffer, stuff like that. So it goes into a lot of detail on various aspects of the basics of network security monitoring, and we'll get into more advanced stuff later as I build out that stuff. Okay, so the other thing I want to talk about real quick is that, so we talk about the repo for ContainNSM. I'm jumping back and forth, I apologize. Is that we have, if you go to hub.docker.com/u for user/OpenNSM, we have a repository available online that you can actually go down and pull these images up. So that the squid is our logo, just an FYI. So you can actually just go, hey, I want to pull in. Let's go to my terminal here. I think that'll be fine. It looks dark. See if I can make it a bit brighter. Oh, okay. So in this case, Docker pull and say I want, go back to here, I want to get TCP dump. You can click on it and you can say tags, and it's got all the tagged versions here. I want to get TCP dump 4.7.4. Well, I can say Docker pull OpenNSM TCP dump colon 4.7.4, and here in a moment it's going out to the website. Docker Hub is going to check for the repository, check if I have it, and then if I don't have it, it's going to pull it down for me, and then I have a container with TCP dump of that version. And it is, network is a little slow here. So, going back to the slides. All right, so now it's time for the demo. So we're going to talk a little bit about the directory structure of the ContainNSM project. So anybody that's in this room can easily contribute to it in the future if they'd like. All right, so let's do a little bit bigger than that. Is there a way we can get a light off in here? Okay, if you can see it just fine. I look at it and I can hardly see it. And it's not a big deal. It'd be the one up here, if anything. So let's take a look at the directory structure. So I have the repo right here, right? So git remote. You can see that I've cloned it here. ContainNSM. It used to be called Dockerfile, so you can actually pull that down yourself, but the new remote is ContainNSM. So again, git clone that link that I had up there. So what we can do here is that we can type tree, right, and then we can do -d-l1, and this will give us all the directories here in this repository. And you can see that these are just the names of tools. It's a very simple directory structure. You just have a directory per tool. Argus, Bro, Daemon, Logger, Snort, etc. And then we'll do one more here. So let's take a look at one of Bro. Let's go in the Bro directory. And you can see there's subdirectories in this Bro directory. And they are the directories named at versions. Very simple architecture. Tool name / version name. And then what's inside of these version name directories? Well, let's take a look here. Get rid of the directory option here and this. And you can see that the hierarchy is a Docker file in each one of these tool directories. And this file has the instructions to build out these tools. And we have automated build set up so that if you commit to the repository and you go to the Docker Hub, you can point to that file and it'll build it automatically for you. And anytime you can make a new commit to this file, it'll automatically update it and rebuild it. So that's kind of nice. But you can build them yourself. So if I want to go inside the TCP dump directory, again, using that as my example, I want to go to 2.7.4. I have that Docker file. Let's take a look at the Docker file, in case you guys haven't seen one before. Very simple file, just has some basic instructions. The Docker instruction set is like, I don't know, less than 20 instructions, so it's easy to get the hang of. You set some environment variables with the env instruction. And you can set labels for organization, but the real meat of it here is down in the run instruction. So this is actually what it does: is it actually creates a container, it runs the commands as you type them on the shell in the container, and then whatever happens after the build process ends, that is your container. So if you say apt-get install mandoc, apt-get install gawk, then once when this file has been read through like a script, then you have a container with gawk and mandoc in it. Very simple, kind of like that. So, and you can do a number of other things. But so basically, all we're doing in these things, we're actually creating, we're downloading TCP dump from source right here. You can see we can configure it, we generate the mate file, we compile it, etc. And then we clean up some of the mess, and then we have a container with TCP dump installed. That's kind of the basic idea. So I want to build this. I have this Docker file. I want to build it, right? So let's do Docker build. We'll say Secure West Virginia. Call it that, and we'll say Docker. Or let's do this. Point to the directory. You can see it's going through that file, running all the instructions. It has a copy and write file system, so it went very fast because it said, you can see it said it used the cache because it's ran this stuff before and it's been stored, so it doesn't have to like go out to apt-get because we already have an image that has that in it. So that's very nice for performance. So at this point, we have a new image, Docker. I can type Docker images, grep, and we say Secure West Virginia, Blam. There's a image called Secure West Virginia. I can do docker run -it, and that says make it interactive, so that it allocates standard in, out, etc., and then allocate a terminal for me. And then we'll say, give it the image name, and then we'll say, hey, I want to run bash. And now I'm in that image. So I'm in a container right now. I can remove all the files, for example, in this container, and then I go back to my host, and nothing's changed, right? It's in its own isolated environment with its own file system, stored in some directory somewhere by Docker. Don't have to worry about it. So you can see that tcbup is installed here, right? So just kind of general example of the containers. All right, so going back. Now, since we saw Docker Hub and we saw the directory structure, you can see it's very simple. There's just a few directories, a name, a version, and then a Docker file in each one of those. So if you want to create a new tool, say, I don't know, what do you guys like? Anybody got any NSM tools off the top of their head? Let's say Silk, System for Internet Level Knowledge. So I can just do Silk, and then I can do, I don't know, whatever version it is. Hey, there's 1.0.1, go in there, right? And then what we'll do is go into that directory, and then we just build that Docker file. And then we're done. We build it, and we commit to the repo, and then I can go in and I can create the automated builds for you. Then everybody has that version of Silk available for download and use. So we're getting to more of the practical applications of that in just a moment here. All right, so you see how that's done. Let's go back to the slides here, and we have another demo. All right, so obtaining, building, and running an image. So we actually did these already. So when we obtained the image, we did that Docker pull, right? And we built the image, we did the Docker build. The command names are very simple to remember. And to run the image, we did Docker run, and then I gave those, the -it options, make it interactive, allocate a terminal, and then you specified bash at the end. Now, we're going to talk about ContainNSM, the proof of concept tool that I've worked on. So this is where it gets more interesting. So at this point, if we go in the repo now, you'll see this tool called ContainNSM. You can run it. It says, hey, use help to get help information. Help information? All right, you can see you got a bunch of subcommands here. You can run help, you can run build, and you have run to actually run various configurations of containers. So the idea of this tool is to make it really easy to take files like input, like pcat files that you want to analyze, get them into a state where the Docker container can read them, and then send the output back to wherever you are. For example, your host, your current working directory. Now, I'm using Docker on OS 10. Docker client is installed. The Docker engine only works with Linux kernels, so you actually have to have that in a virtual machine. So there's the Docker toolbox package you can download on OS 10. And so whenever type Docker is actually communicating through API to the Docker engine running in the virtual machine that's a Linux virtual machine. And this way I can actually get this Docker engine in the virtual machine to read in pcat files from my host and then send me the results back, which is really cool. And it's all done through there. All right, so what we're going to do is we'll do that build example again using the ContainNSM tool because we make it a little bit easier. So we say build, and we just give it the directory we want to build. So I want to build bro 2.4.1, and now I'm building out the image. So in this case, what we're doing here to make it a little bit easier is that we're just pointing it to one of the folders, one of the directories in this repository, and it builds that image. So you can build one yourself if you'd like. I'm going to kill this because it's going to take a while because it's actually going out to the internet and pulling in the packages. So, and then let's continue on. Now we're going to do the run. So do /run or .containNSM. We'll say, hey, look, the run subcommand has these options. So we can say -I and give it an image. So let's do OpenNSM -tcbdump 4.7.4, the latest release. And then we'll say, hey, let's read in a pcat file. And we'll have to give it an absolute path. And I do have a pcat file in my directory right now called nitroba.pcat. So I can do pwd to expand the absolute path here. And then I can say anything passed after the double dash will get to Docker. So Docker will run this. So we can say tcbdump --nnr, no name resolution, and read in a pcat file, and we'll call it nitroba.pcat. And we want to print the first 10 packets. Oops, forgot my run command, run subcommand. All right. Voila. So what actually happened here is I mounted a pcat file for analysis from my host to the container, tcbdump 4.7.4 read it in from the container and sent the output to the host again. So that the ContainNSM helps does this magic. Otherwise, you'd be really long commands. So you can see at the top here, it says it mounted from the host my current directory, repos NSM ContainNSM, to a directory in the container called the same name, and then it changes the current working directory in the container to this repo, and then this is the PCAP that we sent it, right there. And now we have the output here. Now you can go even further and say, well, I want to create a new PCAP file of this with just the first 10 packets. Run it, and now we have a PCAP file in this directory called 10.pcap with those 10 packets that we printed from TCP-dump, right? So remember, we're not even doing this on our host. We're doing this in a container and getting the results on our host, which is really, really cool. So, and just to get an example, what if you if you want to test different versions of TCP-dump, what if you looped through all the different versions that you had and ran this command, just a quick for loop, and then you create, I'm going to actually write it so you can do that in the future to make it really easy, but you can do it now. You have to script it, though. But what if you had group commands? You can type, I don't know, docker group run, and you say bro, and you give that, and then, I'm sorry, not docker, but ContainNSM, something like group run, and then you say, oh, I want to run that, that same TCP-dump image. And then what it would do, and you give the PCAP file, my PCAP, and what happens is it actually launches every single one of the TCP-dump versions on that PCAP file and writes the output to a different directory for those versions. So that'd be really nice, because then you can see what the differences are between, and you can test different options in different versions. That's kind of what I'm going with. That's one of the end goals of all this, is to be able to do things like that, and also pass in various configuration files. And with Docker, you can do labels. Do I have an example here? It might be in a different window, because I always forget. Actually, I think I know what it is. It's sorry, Docker, we can do Docker, what is it? Docker images, -f, and we can do a label equals program equals bro, and that should print all the images that are bro related. So anything that was tagged bro. So in this case, we can say -q, that only prints the IDs, and now what we can do is we can do something like for I in these things, these IDs, do docker run -it, and then we'll say run the image name, and then what we'll do is we'll say bro -- version. I got that right. Oops. Command. It did run that. Oh, that one's so it did run the second one. So that one was one that failed building, because you can see that it says none. It actually failed to build. I didn't notice that earlier. So all we have to do is get rid of that and docker remove, because I was building a bunch of them, just testing them out. Force it in case something used it. So RMI, just remove image. And the image is just the package of the file system with all the stuff in it. And then you take images, and then containers are created out of these images. These things are usually, there we go. So now, if I do this, again, well, let's see, what did I do wrong here? So, so I have a bunch of them that are tagged as 2 or 4. You can see the version 2.3, etc. So I don't want to spend too much time on this example, but that way you can actually iterate through different versions. And again, for TCP-dump, let's do the label example here. Should have a lot of them for TCP-dump. I don't have them on this system, but there's a lot, because I think I have a disk limitation with the virtual machine, so I don't have everything installed. But you could just go ahead and pull them all down. Do I have that? Let's see here. So, like, for example, if you wanted to... Oh, wrong window. This guy's taking forever. Bad internet connection. Yeah, so this one, Docker pool. So all we're doing here is just to give you a few options. Like, we're iterating through the directories, and then we are Docker pull on everything that it's going to actually take the slash and change that to the colon for the tag using a string manipulation in bash, and then it's going to pull all those down. You can see that this is what the output is. Then we just pass that to Docker pull, so it actually goes ahead and pulls down all those versions. So pulling repository, etc. Some of these aren't ready to go, but yes, there's quite a few stuff in here. Go ahead and kill that. Like for the TCP-dump stuff, at this, let's see here. lost my train of thought. Yeah, so you go so many versions of tcdump back to like, I don't know, the 90s or something. But that kind of summarizes what I'm doing here. So again, I just wrote ContainNSM yesterday. Something I wanted to do a little bit sooner, but I didn't have time. But I was able to crank it out. So now we have a working proof of concept, and now from here we can only make it better. So anybody would like to contribute to the project, feel free to reach out to me or the group, attend our meetings, etc. And I think that might be wrapping it up. Let's go back to the slides. And there's a YouTube video online where I do this in more detail. I did for one of the NSM meetings, so you can watch that if you want to build a Docker file or an image from a Docker file from scratch, etc. And my contact information is here: jonschipp.com, @jonschipp on Twitter, Keisterstash on Freenode, and my email address, of course. So, and there are references for all the stuff that I mentioned. All right. Well, thank you guys.